So back to class. Schedule scanning and printing today, and then excuse me, Monday's recitation is going to be programming and debugging. Next week's class is embedded programming. And in that class, you're going to learn how to write code for your processor. And so the first part of the recitation is an intro to programming for beginners to help get started. And then the second half is, in this class, you're going to make many circuit boards that don't work and write many programs that don't work. And so learning how to make them is part of the class, excuse me, but a big part is learning how to fix them. And so the recitation is going to be on intro to debugging, what you do when it doesn't work. So that'll be on Monday, the 26th. This week, we're going to 3D scan and 3D print. And at the beginning, you might have thought this was a 3D printing class. It's one of the things we'll cover, and we'll cover from some of the more advanced 3D printing skills. And then in future weeks, we're going to be revisiting alternatives to 3D printing. So one of the goals of this week is not just to learn about 3D printing, but to learn about the limits of 3D printing. So subtractive machining began in 1952 with the MIT NC mill. 3D printing, there are multiple claims to the invention of it. This is a history article on it. So there's a French inventor, there's a US inventor. It's been invented a few times in a few places. But the key distinction is subtractive machining, you're removing material. 3D printing, you're adding material. Make a note. And that has two huge implications. So one is it's near net shape. Net shape means you're only putting material where you want it. You're not generating a lot of waste. And another implication is because you're adding material, you have access to the interior. So if you want an axle in a shaft, with a 3D printer, you can build up part of the frame around it, and then you can build the axle, and then you can continue building the frame. Subtractively, you need to make them separately and put them together. So just this is linked to some examples. This is a Swiss 3D printer hobbyist who's made a series of beautiful projects like these timepieces, all 3D printed. This is a project 3D printing flexural stages to make high performance microscopes, where the microscope is all printed. And this was a fun project that came out of the Kerala Fab Lab. For small scale machining, in particular for PCBs, this is essentially an all printed milling machine. It's designed so that the whole machine fits in the bed of a 3D printer. And so those are all good examples of what you can do in 3D printing. So one benefit is complexity. It's the same amount of effort to make a solid cube as to make arbitrary complexity. So it makes complexity cheap. You can get access into interiors. You can reduce waste, is why it's growing. Now, the downside is a lot can go wrong. This is Benchy. It is a popular test piece that challenges a number of aspects of your printing. Let me make a note. So One issue with 3D printing is you can fail. So if your filament is old, if you're extruding a filament, if the filament is old, if you don't have the temperature settings right, if the bed adhesion isn't good, you can come back and find spaghetti. If you're using resin, again, with the same sort of issues, you can find goop. If you're binding powders, if they don't bind properly, you can get earthquakes through it. So one issue is just 3D printing can fail. One is the feature size. So for a filament extrusion, maybe 10,000ths of an inch is the feature size of one road. And so what you make is uneven at that feature size. When you're machining, you can machine a surface down to the tolerances of the machine that's typically much lower than a very advanced, that's much finer resolution than everything but a very advanced 3D printer. One is time. Now, there is a, let's see, I think if I linked this, there's a contest to see who can make the fastest benchy. Yeah, no, that is what this is. So this is a heavily hacked machine designed to print a benchy really quickly. And so this is printing the benchy in a few minutes, and it's a pretty terrible print. But that was a few minutes to print a pretty poor benchy. Interesting things you want to do, you can easily spend hours printing. The cost issue is not for beginner printers, but advanced industrial printers. The materials are enormously expensive. You can spend $100 on a small print with the commercial printer materials. You can't print anything. These are two material guides, one from Prusa. Here's another one on the materials that you can print. Our favorite material is polylactic acid. It's plant-derived. It's environmentally reasonably friendly. Oh, let me add another link. I'll explain in a second. It prints fairly easily. It has pretty good structural properties. And so PLA is a good starting material. All of these other ones are stronger or more transparent or higher temperature or more flexible or soluble, but they're also more demanding to print. Outside of high-end printers, oh yeah, there's a link in the chat of an even faster and worse benchy. Other than very specialized printers, you can't print wood or metal on an entry-level printer, but there are fillers that can print wood-like or metal-like material. You need to be aware that almost all of these materials, PLA is the most forgiving, are hygroscopic, which means they absorb moisture, which means you need to store them carefully, and there's a lifetime. If they absorb moisture, you can try to heat it back out, but it hurts the print quality. And then all told, there's about 100 settings for any new material. This is a meeting I ran on open metrology, and this is a talk from my student, Jake, on, we have a paper coming out on a 3D printer that does what's called rheology. It measures the forces and flows in the printer to learn the settings. But for an arbitrary material, there are many settings you need to learn. And so in particular, if you want to use recycle or renewable material, the printer has to adapt to the material, which is why we're working on that. Now, a nice story, and this is a paper that I'll link to this page. Oh, is it not? So sorry, the paper oh no, okay, it is here. Good. I'll put this in the chat, but I'll link this article. This is a nice article on the life cycle of these materials. So it covers how biopolymers can be sourced from plants. But then on the other side of their lifetime, the biopolymers can go back and feed plants. So rather than throwing away your 3D prints, you can use them to feed crops and then grow more biopolymers that turned into more prints. So it's a nice article on closing a circular economy around biopolymers for printing. Now, this is a very important article. What this is looking at is the safety of being around a 3D printer. And this graph is ultrafine particle emission. This is a log scale, so this is exponential. So these are powers of 10. What you see is PLA is low, but as we go up to other material, and up here is ABS, we've gone up many orders of magnitude. So what that means is PLA is office safe. You can sit next to the printer, it's fine. But most of the other specialized materials, you don't want to be around them breathing it. So you want to have an enclosed printer with a filter on the exhaust, and ideally in a room with good air exchange. But there's a big difference in the hazards across these materials. So that's the particles. And then here's a second thing to be concerned about, which is VOC, is volatile organics. And once again, if you start with PLA, the volatile organics are fine. But again, these other materials are releasing a lot of chemicals. So all of that is anything beyond PLA, you want to have an enclosed printer, filtering the air, and having good air exchange where you're working. Let's see. There's a note in the chat about here. About the path planning, and I'll talk about, there's a number of things coming for that. So we can mention that. We'll come back to that. So take away from this that 3D printing isn't harmless. Depending on the material, it's generating hazardous emissions that you need to be aware of in your lab. So next comes the design rules. So you can send anything to a 3D printer, but it can't necessarily print it. And so as a beginner, you just make the design and print it. The better you get, the more you optimize your design for the printer. So first is supports. Let's see, there's some feedback. I'm going to mute everyone. This is an amazing project from Nervous Systems where they designed a dress, and mathematically they lowered the dress into a build volume. Printed that, and then took it back out. Now to do that, there's only one kind of printer that can make it, which I'll talk about in a little bit, which is a powder bed printer, where the unfused powder supports it. Any other kind of printer would be a nightmare of how you support the parts for it. So all these examples, I have a FreeCAD file, I have an JPEG image, and then I have an STL file, which is the most common format for the 3D printer. So what I'm showing here is if you want to print an overhang, that'll fall down. And so for a filament printer, you print a sacrificial structure like that that's designed to pull out. And if it's optimized well, it pops right out. If it's not optimized well, it's really annoying to get it out. But so that's for an overhang. Then what this is showing is clearance. In steps of 1/1000th of an inch, I made the gap between those cubes and the shaft tighter and tighter. And all of these released. But when we got to the end here, those were too close and it stuck together and you couldn't separate it. So that's separating how close can a wall get and you can still release it. Now, supports other than powder printers are the enemy. That whatever process, it can be, there's a tedious labor-intensive task of removing the supports. And so one of the goals is to avoid supports. This was an extreme version. This was a student who, this started as a Fab class project. He figured out that he could starve the printer so it burped, it pulsed, and then he could use that to build up textiles. And on an ordinary printer, he could make these beautiful fabrics. And I'll come up to this was, I forget how long this was. I want to say a week, but I think it was longer than a week. I think it was a few weeks of just the printer. This was all a single print. And he unrolled it from the printer. This 3D printed fabric done without supports. And then he went out to MIT sports field. And this is the size of the sports field. And in fact, it's even longer than you can see. He reached the limit of just how high he could fly the drone. So that's a dramatic example of printing without supports. So this is the most important design rule. What I'm doing here is I'm stepping an angle. And you see vertical is fine. If I try to print horizontally, I get spaghetti underneath. But around about 20 degrees, it's happy. As long as you have a little bit of an angle, like 20 degrees, you can keep building out even though there's no supports. So this is one of the ways you eliminate the need for supports, is rather than flat overhangs, you have angled overhangs. Then here what I'm testing is how far I can go before it degrades. And after a very short distance, I get a mess underneath. But the other really important design rule is bridging. Here what I'm doing is I'm building up in layers. And then when I get to the top, if I go out and stop, nothing is supporting this and I get a mess without supports. But if I build up here and I build up here, I can pull from here to here and reconnect. And so these were done without supports. And you can see I can bridge over a surprisingly long distance. And so if you want to have like a door in a house or windows, you don't need supports for that because you're bridging. So with those two design rules of the minimum angle for an unsupported growth direction and bridging for a horizontal growth direction, just with those two tricks, you can, to a great extent, avoid the need for supports. Next is, this is using a high resolution printer, a stereolithography printer. And what I'm doing is I'm stepping down how skinny a wall I can make and how small a gap I can make. And this is this was done on a Formlabs printer. This is a nice printer, a filament extrusion printer. Can't make features that fine. Another one to be aware of is, this is printing a test shape with an inside dimension and an outside dimension. And depending on the printer and the slicing software and the filament material, there can be a significant difference in size between what you designed and what you get for the printer. And so an important test is just measure the dimensions you give to the printer versus the dimensions it gives to you. And typically that's much worse than machining. For strength, typically the printing is done in layers. And so if you take just this structure, if you pull vertically here, it's pretty easy to delaminate, to peel the layers. If you pull horizontally here, it's stronger because you're pulling in the direction of the filament. So the mechanical properties are a function of direction. This is just showing, as a function of angle, the surface finish is more noticeable when you're at a shallow angle where the steps are more clear. Then this is varying the infill. If you make it hollow, you build quickly, but it's weak. If you make it solid, you take more material and it's slower, but it's stronger. And so you can decide how much infill you want, varying weight, time, cost, and strength is a design decision. Then if you have a sharp corner, that's terrible, because what you'll get is there's one pass there, and then maybe two here, three here. And when you print that, all of that just becomes a tangle. So you don't want sharp edges. You want to facet it so that there's enough passes of the printer so that it supports the end. You want to avoid sharp features as a design rule. Next, so right now I'm describing filament printing, which is what most of you'll do. I'll come back and talk about other processes. In filament printing, there's a filament coming in, it's melted into a head, and it's extruded. If the head is too close to the bed, there's nowhere for it to go, and you get terrible printing. But if the head is too far from the bed, it doesn't adhere, and you get spaghetti. So the distance between the head and the bed is a very sensitive parameter. And you need to get that to better than 1/1000th of an inch. It's a very sensitive parameter. Typically, the beds aren't perfectly flat. They can have a little curvature. So what good printers do is they dynamically probe the bed. They make a mathematical map of the height and adapt to it. If you don't do that, you'll get bad print quality. And even entry-level printers know how to do now. So it's very important to have a printer that can map the bed. Even then, depending on what you're printing, if there's bad adhesion between your print and the bed, as you're printing, eventually it can come off and you get spaghetti again. And so there's a number of things you can do. Some people use an adhesive layer. I don't recommend that because the adhesive becomes sticky and gooey and accumulates. I prefer the opposite, which is to make sure the bed is completely clean, to remove all the oils and any residue on it. And then one thing you can do is what's called a brim, where you print a lip that goes beyond your print that's easily trimmed off but improves the adhesion. You can also make what's called a raft, which is a layer that supports your part that goes from the bed into the geometry of your part. And so if you have trouble with bed adhesion, rafts and brims can help with that. Then when you're done, there's a lot of post-processing you can do. So this is a smooth-on material that's designed. You don't have to use this uniquely. You can use a number of different materials. But this is like an epoxy that's designed to be spread over the print and interpolate the roughness from the printing process to give you a smoother surface. And an interesting process you can do is electroplating, where this is a resin part turned into a conducting part by putting it in a bath. And you can do metal plating on the polymer part with an electroplating bath, which is reasonably friendly chemistry. It's not that sensitive. There's a note in the chat about Brigitte doing 3D printed textiles. Oh, I have to log into Instagram, but it's in the chat. So how do we print? Let me make a note with an edit. So Shapeways is a service bureau. It's a good reference because they run one of just about every kind of printer. And so they have a nice trade-off you can see of parts made in each process and how these each relate to each other. So among printer types, 3D Systems was started by one of the inventors of stereolithography. And so you have a resin bath, and you either scan a laser or you project an image, and optically it binds the resin together where it hits. Then you wash off the uncured resin. And this is, I'd say, right now the highest resolution process. Then the founder of Stratasys was one of the inventors of what's called fused deposition modeling. And that's a commercial proprietary term. So FFF, fused filament fabrication, means the same thing. There, you're extruding a polymer. There's a lot of tinkering with the design of the extruders. And this is, there's been a trend moving from 0.4 to 0.6 millimeters. There's a lot of different objects you can extrude. So in addition to polymers, these are colleagues who make printers that extrude clay to make these beautiful structures. This is a colleague who extrudes concrete to make buildings. And so that has good structural properties. It's used in the most accessible printers. This is an emerging process where you take a metal wire, and at a higher temperature, you melt the metal wire to do metal printing. Z Corp developed, this is part of inkjet, and make a note, Desktop Metal do what's called binder jetting, where in binder jetting, you spread a layer of powder and then you print something that sticks it together. And so for metal, you take it out and then you need to sinter it in a furnace. One of the interesting processes with binder jetting is to use wood powder, and you use lignin as the binder, and then you just leave it like that. And it's essentially making reasonable quality wood parts. Polyjet is a process where you print little droplets of an ink that it's like inkjet printing but in 3D, and then you optically fuse it. That makes among the highest resolution parts, and in particular lets you do color. Selective laser sintering is where you spread powder. Oh, let's see. I'll have to fix the. You spread powder, and it can be nylon or metal powder, and then the laser sinters it together, and then there's no other there's almost no post processing. You take it out, you shake off the unsintered powder, and then clean up the surface. There's a question about 1 micron. So let's see. I'm making notes to add. So laser stereolithography, as I described, is the light comes in and drives the chemical reaction. 2-photon printing uses a reaction where rather than one, you need 2 photons to stick it together. And what that does is it enhances the resolution. And so these, the 1-photon systems right now today get down to about 20 micron feature size. To get below that, you need the 2-photon systems. There's a lot of work currently on bioprinting, where you extrude biologically active material. This is a link to a meeting I ran many years ago that's still ongoing, but that's about what you can think of as digital printing, the transition from extruding to assembling. And a lot of the research in my lab is about processes for that. So with those processes, now let's look at some of the interesting machines. So RepRap was started years ago by a colleague, Adrian Boyer. And his real interest was not simply in printing, but he was interested in self-reproduction. And so the RepRap was designed to be a machine that could make its own parts. And there's a fun picture of the RepRap parent machine with the RepRap child machine. So RepRap in turn spawned many different projects. So Ultimaker started in Fab Lab in the Netherlands, aiming to speed up the performance of the RepRap. And one of the most interesting projects they did was, this was from Utrecht. They put the printers on a moving Z gantry, so that as it printed, the printer actually lifted up, and they printed an elephant. So they weren't limited by the bed size of the printer. The printer actually lifts up as it prints to print something bigger than the bed of the printer. Prusa did a really interesting job of taking that, let's see, let me make a note. Interesting job of taking the RepRap descended design, and it's an open source design. You can download all of their files, but they support it commercially. You can buy a kit or you can buy a finished printer. And they've done a really interesting job of trading off an open design that's a shared design. And one of the interesting parts of their machine is they run a crazy print farm of hundreds of their machines making their machines. So this giant print farm, any one of these is fairly slow. but they have hundreds of them cranking out parts of machines to make more machines. And so all of these parts were done on the Prusa, my design parts. SaneSmart took essentially the Prusa design and just did Shenzhen style cost reduction. And so they've got it down to a few $100s. The first ones had all sorts of issues, but now they do automatic bed leveling. They have metal drives. They're now surprisingly good, reliable. Bamboo was drone engineers who looked at 3D printing and said, we can re-engineer it better. This is about $1,400. That's the one behind me. And they've done a really good job of making a automatic feeder that lets you switch filament in the middle of prints. And they do a really good job of controlling the environment in the printer, measuring everything in the environment, and then automatically tracking it and following it to it. So this is doing those same parts on the Bamboo, and this is printing with 2 different color filaments with the material changer. Let's see. Actually, let me go to first. So Formlabs was started from students from my lab, and they wanted to make resolution accessible. Let's see, Leo, in my experience, we do the Bamboo with students. It's not repairable, but there isn't much that goes wrong. It's well engineered. So we have students using it, but it's not easily hacked. So Formlabs was started to make stereolithography accessible. And so here's the test parts. And again, you can see the resolution, the quality of the prints done with the stereolithography versus the FDM printing. And then some of the fun things are, there was an interesting historical battle. These are Max and David founders. This is a nice video on the birth of Formlabs and the lawsuit with 3D Systems. This is an amazing project where they, this was a stop motion movie where every frame of the movie is a part. So he did this insane project where he's printing every frame of the movie and then doing stop motion from that. And then, yeah, there's a question about rubber. If you look at, I'll talk about vendors in a second. So let me pause for that. This was a really interesting project where they're mass customizing selfies where they're printed on the Formlabs machine. They develop resins that match skin tone, and then they're using a UV Cure printer to print on the surface to do the color on the surface for mass customization. And then more recently, Formlabs has come out with a selective laser sinter machine. And so that laser sinters nylon. And what's so great about it is, unlike all the other processes, there's no need for a support. The unsintered powder automatically holds up the sintered powder. And so this one lets you make really complex things like meshes. Then Elegoo, thanks to our friends in Shenzhen, have been developing low-cost stereolithography printers at high resolution. And so these are down to the pixel, sort of you could say the voxel size is 20 microns. That's really the pixel size. The actual size is bigger than that once you get through the whole process of the chemistry. But this is close to the state of the art for 1-photon stereolithography resolution. So this is a less friendly process compared to extruding PLA. It's sticky, it's gooey, it needs ventilation. You make chemical waste in washing it. So I don't recommend this as the day-to-day workhorse printer, but I do recommend having this in your lab for where you need higher resolution feature sizes. Then one of my favorite printers is this one from Stratasys, the J55. So this does the polyjet process where it prints with little droplets of material, and it has multiple feeds for it. And so all of these came out of the printer like this, that you can print supports for microfluidics, but one of the killer apps it can do is with the multiple droplets of material, it can print color. And this is now real volumetric color. It's not just the color on the surface, it's color in the interior. So that's one of the nicest printers. The downside is it's about $100,000 machine, and the materials are proprietary and equally expensive. So this makes sense in a higher end super lab. It costs as much as a regular lab. There are a number of versions of DIY open printer designs in machines started by Danielle and Gracia, a student from the class, has made this printer. This is a really nice project making a hanging printer. So you set it up in a room with tendons going to this hanging print head, which lets you print beyond the limitations of fixed bed size. This was an experiment making 3D printed axes, and we'll see more of this when we get to machine building. Precious Plastic makes the opposite. They make a series of machines that take waste plastic, grind it up, extrude it, and then can turn it back into filaments. And Philastruder is another project making, again, the reverse process, which was a tool that lets you take waste material and feedstocks and produce your own filament. Important looking ahead to closing waste so you don't throw away 3D printing. Now, for the materials, these are a few vendors that all sell a wide range of materials. And so to the question in the chat, you can start with if you want it to be metal-like or wood-like or reinforced or soluble or flexible. And there's a really great selection of these. One of my, let's see, I don't know if I have it linked, but one of my favorite is let's see, making notes. So this is a really interesting material. This is wood fiber in a partially wood resin. And when you're done, it makes wood-like parts. It's not like lumber from a tree. It's closer to some of the materials we'll learn about in the 3D printing week, but it comes surprisingly close to letting you 3D print wood. Now, those sort of materials, the thing to know about is they can be much more fussy to print. They can also be abrasive to your printer. You can need things like stainless steel feeds for them. They can be very hygroscopic, so how you store it is important. But with those notes, there's a range of material properties you can get with those. A nice thing you can do is, along with printing fabric, it's really easy to 3D print on fabric. It works great, and so you can 3D print features that become part of the fabric. Is a nice process. Yeah, Leo's asking about a fifth axis. I'll talk about, I haven't seen much on adding axes to printing. There's a lot on the path planning I'll talk about in a minute, less on that. Now, a common and important question is, these are 3 different sites, one from Formlabs, one from Prusa, one from Hackaday, all of them looking at food safety. And so food safety in 3D printing is a little bit like being kosher, meaning all the steps of the process have to be food safe. The material printing has to be done without mixing chemical. You want the pathway it goes in the printer to not have seen unfood safe material. You don't want to trap, you want to make sure you can clean it. So those are all links on food safety. And then service bureaus, these are all vendors you can send jobs to when you either need more specialized printing or more printing. But one of the things I'd recommend in your labs is set up a print farm. So the maturing entry-level printers are just a few $100s. And so for a few $1,000s, you can set up tens of printers in your lab. And print farms change how you use the 3D printer. Once you have a print farm set up, there are many more parts that would take too long that you wouldn't do on one printer, but that you can just get printing. And so when we get to things like machine building, I really recommend investing in at least a few printers to have an in-house print farm. So those are printers. Now, to send the job to the printer, you have to give it a file. Far and away most common is STL that came from 3D systems. It's barely a file format. It's just a list of triangles. You can do them in ASCII. More common is binary, that's more compact. If you're comfortable programming, it's very easy to write STL files. So you can write your own algorithms to generate them. Every printer understands them. What's bad is there's no way to specify color or material properties. You can't even specify the units. So you have to tell it what the units in the file are, like inches versus metric. But other than that, it's straightforward. Everything understands it. That's most common. Ply adds color. 3MF is emerging as a successor to STL. That's a very long industry process. That's a container for multiple formats. OBJ is an Autodesk format, but it's widely used in multi-material printers to describe things like color properties. Some more advanced printers let you give voxels. So rather than triangles, you actually give volume elements to describe complex geometry. And then the most common FDM printers take G codes as a format in, an ancient format that I'll complain about when we get to machine building. But standard printing is done in layers, but there are lots of versions of this is printing not in flat layers, but curving the surfaces to get better surface finish. This is building loopy arcs to make overhangs where I said you can't make overhangs. This was a fun project from the VOG, which is doing real-time control over a printer, in that case, as a excuse me, musical instrument. This was something in the chat I hadn't seen, which is instead of layers, by offsetting layers like you do when you're brick building, you can significantly improve the strength of the printing. That's a nice insight. So all of that is beyond just printing in layers. So to do this, the first thing you need, so you're going to produce a file for the printer, most typically an STL. These STLs can grow very large. This is one case where your STL can be bigger than what we allow for the size of a commit 10 megabytes. And so if you have very large STLs, you can put them on a file sharing site rather than on your own site. And in the CAD week, I had covered, for example, GrabCAD lets you can put designs on GrabCAD, and then you could put a viewer in your site to see it. So these tools, you're going to need one of these kinds of tools. MeshLab is one I like that's open source, freely available, cross-platform. What these let you do is take a mesh, view the mesh. You can do surgery on it. You can up or down sample it. And so you want to have one of these tools just to be able to understand your message, your meshes. Then this has really matured. So Replicator G, Skynford, Slicer, Prusa Slicer, Cura, all of these are Slicer projects. Almost all of them now work with almost all the printers. Oh, let's see. I have to fix. That's a broken link. So this is Cura. This is Slicer. What these do is they take your design file and they figure out the path for the printer. And over the years, they've gotten much more sophisticated for things like how you follow the perimeter versus you fill the interior, strategies for the design in the interior. And I'll show you some fun examples of that. How you moving from printing in layers to non-flat printing. And so the printer you're using typically have a recommended one, but these have all matured, all become very powerful. Print Run is an open source controller for G-code printers. And then Octoprint is something to manage a farm of them, to manage a network of them that I recommend. Oh, and actually I've got this here. So Sketchfab, Thingiverse, Model Viewer are all ways that you can share your designs with 3D viewers in your web page. So that's preparing the slicing. And so for 3D printing, the group assignment is test the design rules. You can use my test files here. There's a number of other test files you'll find, but I want you to check how skinny can a wall be, how flat can an angle be, how close can surfaces be, how sharp can a corner be. Learn the design rules and use that to design. And then the 3D printing assignment is I want you to design and print an object, not too large, a few cubic centimeters. That's going to be limited by the just time on the printer. The key part of this week's assignment is I want you to design something you can't make subtractively. So we've done machining. 4-axis machining is where you can rotate the part. 5-axis machining is where you can rotate the part in 2 axes. But you can't have an outer shell and a cage and a part inside the shell. Or you can't have a part that comes down and has a channel into the inside. And so as a design exercise, you can print anything, but I want you to design something that can't be made on a milling machine. It has to be a design that you can only make additively, because of the design features. Okay, now we're going to go to scanning. 3D scanning is the opposite. Oh, let's see. Hank in the chat is pointing out, I'll add a link. For filament printers, Clipper is common embedded software, the software that's taking the G codes and talking to the printer. I'll add a link to that. Now, 3D scanning. So that's the opposite. 3D scanning is, this is a 3D model of me and my fleece and my chair. It's getting something back into the computer. 3D scanning has been improving, but can be frustrating. So not always, but typically what you get from the scanner starts as a point cloud. It's just dots in space. Then typically the workflows need meshes. So you need to turn the dots into triangles. Often the scanners miss places. So you need to patch up holes to make it what's called watertight. So if the mesh has holes, the printer doesn't know what to do. And if you have a color printer, you want to know what the color on the surface looks like. So you want the texture. All of that can be a strong function of how you light the sample, what's in the background, and what's in the surface. So I'd say the best, oh, let's see, I have to fix the link. I'm not sure what happened to that. So this is an X-ray microscope in my lab. It does what's called a radon transform. And this is what it can do. This is a fly-through of the head of a housefly. So this is 3D scanning a housefly, and it's showing you the inside as well as the outside. So it's doing 3D tomography. So that's wonderful. The biggest challenge with that is it's a few $100,000. So that's only in a really advanced research lab can afford that. Actually, it's coming down in cost, and I'll add, this was a startup to make lower cost tomography. And rather than selling you the machine, they sell the tomography. You buy it, and it's reasonable for a research lab. It's maybe a few $1,000s a month to have one of their systems to do tomography. This is an atomic force microscope. It has a probe that it drags over the surface, and it measures the surface at atomic resolution. You can do that at less than atomic resolution. And so these are completely immune to surface artifacts, very high resolution, but it's not arbitrary 3D geometry. It's 2.5D, meaning it's giving you Z as a function of X and Y. So that's scan probe. This is a tool in my lab that's called the confocal microscope. What it does is it moves an optical volume through space, and it sees where the optical volume hits. So it's non-contact, you get optical properties, and it does it to the resolution of the microscope, which can be about 1 micron. This is the state of the art in working out the wiring of a brain. And that was done destructively by, in a microscope, making a thin slice, taking an image, and destructively nibbling away at it. So if you can grind away your sample, you can destroy the sample, but scan it. And that's nanometer resolution. This is what's called a milk scanner, and because it started literally as that. What you do here is you pour an opaque liquid and you submerge the object, and then you watch the boundary as the object disappears. And so that's one way you can scan people. Roberto is asking about superimposing scans. Roberto, a tool like MeshLab, one of the things it does is you can take multiple meshes and merge them. That helps, but typically the holes come from problem places where the light doesn't come back out. So no matter how you scan it, some places you always have problems. Then this is a coordinate measuring machine. This is an arm. And so this seems like it could be annoying. What you do is you manually touch it and you click a button or a foot pedal and you touch different places. But what's nice about this is instead of scanning automatically, you figure out where to scan. And so this is used, like when Frank Gehry makes a model of a building, this is used to digitize it because you add value in the scanning process. You add value from where you probe it to just get the most relevant points for the design. So those are useful. Then photogrammetry is where you take a lot of different pictures and then you solve a hard math problem, which is what. So you just take lots of pictures, and then the question is, what is the object and what is the camera position that explains all those pictures? So Alice Vision is a photogrammetry pipeline. Meshroom is a tool for doing photogrammetry. And one note is this needs a fair amount of computing. It wants a computer with a good GPU. And then the other note about that is it's aspirational, meaning it's trying to interpret the scan, but what you get back can be quite a bit different than what you gave it. And let's see. This was a project student Quentin did to improve photogrammetry, where instead of you just randomly taking pictures, it moves a camera through a known position. So you have evenly spaced pictures and you know where the pictures were taken. That improves it. So photogrammetry, what's nice is it just needs an image, but it can have a lot of different artifacts, and it can be very, it can also be qualitative, that there can be a significant difference between the object and what you get. A speckle is where you send a dot pattern out and then you look at the dot pattern. So rather than just taking an image, you're illuminating, but you're illuminating with a random dot pattern and you're looking at what happened. And so Reconstruct Me. So that's historically how, oh, that's a broken link. This is software, I'll fix that link, that takes the Connect and then uses that to reconstruct. This is a laser scanner. So in a laser scanner, you send a laser beam to the object, and then you look at where the laser hit the object. This is a FabScan open source project. That works well as long as there's good reflectivity for the laser beam to come back to you. That doesn't work well on shiny surfaces. It also doesn't work if the surface is angled away. So the laser beam is deflected and so you don't see it. Structured light is you illuminate, but rather than just a random dot pattern, you put a known pattern of light and you look at how the light pattern bends. And so here, let's see, I'll have to fix these links. What I'm linking to there is there are laser pico projectors. Yeah, I'll find a better link for that. Where they project with a laser beam, and what's good about that is you don't need a lens to focus it. It stays in focus no matter how far away you are. And so this is an example I did a while ago where what I'm doing here is I'm projecting what are called gray codes. So a binary code, when you count up, suddenly all the digits can flip at the same time. A gray code is a neat algorithm where you always flip the same amount. And so what I'm doing here is, as I put this pattern, you can see the bending of the beam tells me distance. And then by varying the gray code, I'm measuring it at multiple scales. And then you can combine those measurements together to give you topography. So that's a structured light scanner. This is a commercial yeah, there's a lot of turnover in these, which is why all these links are broken. Then stereo is where you have, you're seeing in 3D because you have two eyes. And so this is a family of stereo cameras. And this right now is my favorite 3D scanner. So this is from Creality. They've reduced the cost to a few $100s. They're using a custom chip to do the stereo vision. And this is what I showed at the beginning. So this is me. This is my fleece. This is my chair. I'm not showing the color, but it also, oh, actually, sorry, I'm showing the color here. So this is the texture. So it gets color as well as geometry. And the combination of the maturing of their software and the custom chip is, it's surprisingly robust. In my lab, the Artec Leo is the $30,000 expensive scanner. And I'd say this $400 one works about as well as it. I'm really impressed with that. Then LiDAR is like radar, but with light. It's where you send out light and you measure the time for the light to come back to you. And light travels a nanosecond per foot, which means to resolve optically, you need to measure picoseconds. Very, very high resolution. But there's a number of devices emerging that does that. And the most interesting one are cameras. So a LiDAR camera, each pixel is like a little radio receiver. You send out the light, but you modulate the light with a waveform. And then each pixel measures the modulation, the phase of the modulation. And by doing that, the pixel is measuring not just image, but distance. And that's just now starting to come into phone cameras. So Apple has been pushing out LiDAR in its newest phones. And Scaniverse is a tool that doesn't require it, but it can talk to it. And so LiDAR, so this has been very much in flux, that the companies that make it keep being bought and sold and reconfigured. But LiDAR, I expect, is going to displace all the other kinds of scanning because it's not using derived optical properties. It's actually using just the basic physics to measure distance. Now, the best scanning of all is, this is me and my son Eli visiting Paul Debevec, a colleague at USC. And what he's doing in this giant structure is each node is both a light and a camera. So he can light from any direction and he can image from any direction. And I look the way I do because light bounces off the surface of my skin. It bounces below the surface of the skin. Some of it is specular and some of it is diffuse. There's color, there's also texture. All of that goes into why I look the way I do. To do that, you need to measure from all angles. And so this is a link to a project where they made a tabletop light stage. I'll skip that for time. This is a link to the research on it. That's the state of the art in photorealistic scanning. That's used for things like making completely synthetic actors you can use in a movie. And then finally, SLAM is simultaneous localization and mapping. And that's where, rather than scanning an object, you're continuously scanning your environment. Let's see, I see Yuichi in the is showing a 3D scan of his whole lab done in Matterport. Oh, let's see. I'm in it now. I can navigate through his lab. Very nice. So that link's in the chat. So SLAM is where once you have a phone that can, or a robot that can do one of these kinds of scanning, you do it continuously. And as it moves around, you're building a model of the scene. And that's needed for augmented reality, which is what's driving it commercially. So the scanning assignment is scan an object. And you can experiment with all of these. And in particular, tools like these consumer stereo scanners have made it much more friendly, much less annoying. And then optionally print the object. Going from a scan to post-processing to printing it is a non-trivial task. And this week, you're going to be limited by time on the printer. So get the printers going on the prints that can't be made subtractively, the ones you design. And then if you have time, go back and print the object to scan. But the main goal this week is just meet the scanners in your lab and experiment with these options for scanning. And of them, both the low-end consumer ones and the phone software keeps getting better and better. And so it'll be interesting to compare those this week. So I'd say last week was one of the least creative weeks. This is one of the most creative weeks. It'll be a fun design exercise to design something that you can't make by removing material. Do your best to try to align it with what you're going to need for the work to come. Look ahead to your final project. And then, as usual, open time Saturday with the great team supporting that. It's available for any question on anything. And it's also a good way to get to know the community. And then we will meet for a recitation Monday, the programming intro, and then the debugging intro. Getting ready for next week, we'll start writing embedded code in the processors. Okay, happy scanning and printing. This is a fun week. I look forward to seeing what you all come up with next week. Bye-bye.
Bye-bye, everyone.
Bye-bye.
Assalama.
Tack alla för er.
Bye.
Nos vemos. Chao, chao. Chao, chao a todos.
Hasta pronto.
Bye bye.